Hello, my name is Darren Lipomi. I'm an associate professor at the Department of NanoEngineering at the University of California, San Diego. My research group studies the mechanical properties of organic semiconductors for a variety of applications, but in this talk I'm going to focus on the application of mechanically robust organic semiconductors in the production of robust organic photovoltaic devices. Okay, so most of the people in this crowd are familiar with the fact that organic solar cells have achieved benchmarks in the literature that were really considered out of reach maybe 10 or 15 years ago. So solar cells at the lab scale are now more than 10% efficient, and the charge transport properties of organic semiconductors are better than amorphous silicon under favorable conditions. This is an image of plastic solar cells produced by the host university, Professor Krebs' group at the Danish Technical University. And these cells were deployed in rural Africa as part of the Lighting Africa initiative. So the idea was they could be printed on an 8.5 by 11 inch approximately sheet with some LED lanterns at the top, so that kids in rural Africa could do their homework and read at night without resorting to burning kerosene and unsustainable biomass. The authors noted in this project, however, that mechanical failure mechanisms were dominant during the field test, and in the actual experiment where around a few hundred devices were deployed in rural Zambia, most of them that were returned to the researchers had evidence of mechanical failure. Moreover, a few years ago at the combined workshop of the National Science Foundation and the Office of Navy Research, one of the conclusions of this, or one of the unanswered questions in this symposium was, do organic solar cells fracture cohesively or at interfaces, and what has been done to prevent these devices from failing mechanically? So my group is not the only group to be interested in this problem. In particular, Brendan O'Connor's group at North Carolina State University has published a very striking correlation between the spectroscopically determined order in an organic bulk heterojunction blend, so that's percent aggregate and the order parameter, don't worry about the details, and the efficiency. So what we find is that the order goes up, the efficiency goes up, but the stiffness, as manifested in the tensile modulus, also goes up. So the researchers also published an analogous study of the brittleness. So as the efficiency goes up, the order goes up, and the brittleness in the form of the crack onset strain on an elastic substrate also increases. Now, I also want to mention that Reinhold Dosgaard's group at Stanford has also been one of the leaders in this field in measuring the cohesive and adhesive fracture energies of printed modules and other devices under shear strains and pull-apart forces. So this is sort of the near-term goal of our research, but just because I'm meeting some of you for the first time, I'd just like to mention that we are also interested in sort of the longer-term applications of organic semiconductors in the form of organic bioelectronics. So the idea is, if you can make organic electronic materials more like biological tissue, then you can start to envision applications in robotics, instrumented prostheses, and electronic skin that have mechanical invisibility. That is, you can't feel them because they're so compliant. Now the problem is, again, if you zoom in to the surface of the organic semiconductor, this is an atomic force micrograph of an organic semiconductor. This is a P3HT PCBM blend at 20% strain. You can see significant mechanical failure. So one of the major challenges associated with measuring the mechanical properties of these materials is that they are almost always used in thin film forms. So films that are less than 200 nanometers thick, or at least less than half a micron. So it's very difficult to get the mechanical behavior from a traditional pull test. And the reason is because, number one, it's hard to manipulate a freestanding film, and number two, if you're working with synthetic chemists in your research group, you might only get a few milligrams of material at a time, so it's very difficult to form a bulk piece to get a tensile test. So we can measure the tensile modulus using this film on elastomer method, where one compresses the film under a small tensile strain and converts the buckling wavelength and the film thickness into the tensile modulus. You can get the crack onset strain, which is a measure of the brittleness, by putting the film either on a linear actuator or on a bendable substrate for a low strain regime and the high strain regime. And that gives you an idea of the fracture energy. And you can even approximate the yield point, first by putting the structure of the film on an elastic surface and then increasing the amount of strain incrementally, so from 0 to 1% to 2%, back to 0, back to 3%, back to 0, back to 4%, back to 0, and so on. Now, as soon as that film experiences plastic deformation, the film will buckle when it's returned to 0%, and you can observe the buckling either optically, but sometimes optical wrinkles are difficult to detect by microscopy, so you can shine a laser through them and detect the diffraction pattern on a screen, and when you see that, you know that the film has surpassed its yield point. Now we can put all of this information together to generate a rough sketch of the pull testing behavior, or the behavior that you would observe normally by pull testing. Now you're not going to get this exactly right, but you can at least get the principal features. So the slope in the elastic regime is the tensile modulus. The yield point is determined using this technique, and the strain at fracture is determined by the crack onset strain. Now the area under the curve here is the resilience. That's the amount of energy absorbable per unit volume by the material in its elastic regime. When that amount of energy is surpassed, then the material plastically flows. And if, assuming this point is not way up here or way down here, we can get a rough estimate of the toughness, that is the total amount of energy density absorbable by the material until it finally fractures. Now what does that look like? If we look at just the fruit fly of organic electronics, that is poly-3-hexylthiophene, as a function of molecular weight, so this is done with Professor Martin Heaney at Imperial College, and we plot the tensile modulus, just to take an example, as a function of molecular weight. We can see a trend. We don't expect a monotonic trend here. We expect some kind of unusual behavior that is a manifestation of multiple effects, because at low molecular weight you might have a greater crystallinity depending on the material. This is just one effect. But you also have, which could increase the modulus, but then you have fewer entanglements. So it's not a simple relationship. So what you could do is plot the tensile modulus, the yield point, and the crack onset strain in this sort of confusing way, or you could convert it to a plot that looks sort of like a conventional pull test. So we see low molecular weight stuff has a low modulus, low crack onset strain, low toughness, and low resilience. As you increase the molecular weight, you're able to stretch the material out more and increase the deformability. Okay, so that's kind of an intuitive answer that we know from the engineering plastics community of the effect of molecular weight on the mechanical properties. Let's look at some of the molecular effects. In particular, if we look at just the poly-3-alkylthiophene and the C60 PCBM, and in both the neat form and the blend with the two materials, and we look at just the function of the alkyl side chain length, we see that the tensile modulus goes down with increasing side chain length, and we can rationalize this observation just by considering the fact that the longer the alkyl side chain length, the lower the density of load-bearing carbon-carbon bonds along the strained axis, so that makes the material more compliant. If you look in particular, there's a big difference between C6 and C8. There's about an order of magnitude difference represented here, and we'll get back to that in a moment. The same effect is observed in the crack onset strain. So the material undergoes an increase in ductility and then a reduction in ductility. Here, we don't think this is actually a real effect on the material of the material. We think this is because the adhesion of the film with the substrate actually decreases as you increase the length of the side chain. It becomes more hydrophobic. Its van der Waals coefficient goes down, so the adhesion is not as good, and therefore we think this is a result of strain concentration at thin areas and defects that one observes in poorly adhered films throughout the film on foil or film on elastomer literature. And this is consistent with the fact that the water contact angle increases as a function of the alkyl side chain length, which is indicative, or which is usually consistent with poorer adhesion. If you look at the strain at which yield occurs, we see an increase in yield point. Now this is all approximately the same molecular weight, about 30 to 40 kilodaltons. And we note again that the largest increase in deformability occurs between the C6 to C8 transition, where the modulus goes from over a gigapascal to almost, but not, or to about 150 megapascals. So using this knowledge, we can do something just by using the molecular structure. We can take a whole organic solar cell and stretch it over a surface with a complex topography, other than a cone or a cylinder. So a cone or a cylinder, you can just bend it. But if you want to put a solar cell on a hemispherical surface, you need biaxial stretchability, not just bendability. So the idea was to make this inverted solar cell architecture with P.PSS and PEI to lower the work function, and P.PSS as the top contact. And the finite element model said that we needed about 24% strain to accommodate this transfer. And we can see that, so our analysis in the previous slide said that the C6 polythiophene would not survive this transfer, but that the C8 polythiophene would. And that's what we see here. The P3, the C6 polythiophene is cracked, and the C8 polythiophene gives you an intact device. Now, poly3-octyl thiophene is not regarded as the state of the art in organic semiconductors, mainly because the larger the side chain, the more diluted the volume fraction of semiconducting material, and you get pretty lousy solar cells. So the idea was, could you make the best of both worlds? And these are just different geometries, different light angles, and from the top or the bottom, and so on. You can look up the details in our paper. So the idea is, can you generate the best of both worlds, but just by tuning the side chain? And so this experiment is facilitated by the fact that one produces poly3-alkyl thiophenes in a step growth quasi-living polymerization using the Grignard metathesis polymerization described by McCullough and Ricci independently, but this is McCullough's method that we show here. So it's possible to grow the chain using monomers with different side chain lengths. So what we did was we looked at the physical blend of P3HT and P3OT, a block copolymer of P3HT and P3OT, and a random or statistical copolymer of H and O, or C6 and C7, or C6 and C8. Getting ahead of myself. We actually also looked at the homopolymer C6 and C8, but also C7. So what happens? We find that C8 has a low modulus, which is good, generally indicative of more easier deformability and lower interfacial stresses if we have a lower modulus. Also for these materials, it tends to correlate with the same molecular weight with ductility, which makes modulus a useful proxy in this case for many mechanical properties. Efficiency is low, which is bad. So we want to be somewhere up here. We know that C6 is stiff, but it's more efficient. The block copolymer gives us nothing. It's a pure compromise, so we're not up here. The copolymer starts to occupy this space. The physical blend, where we do no chemistry whatsoever, is even better, but the best one overall is C7. So that's the best of both worlds, and here comes the sun. Now we can rationalize the mechanical behavior based on the fact that for comb-like polymers, there's an effect where the glass transition temperature goes down with an increasing length of the side chain, and that's what we see in the polythiophene. So between C4, 5, and 6, there's a big drop-off in tensile modulus between C6 and C7. Now that's really an artifact of where the glass transition tends to be, and it's above room temperature for C5 and below, and greater for C7 and above. Or glass transition temperature is below room temperature for C7 and above. C6 is very close to room temperature. It's probably not always above. It depends on how cold your room is. So this is really a borderline case. C6 maybe has a glass transition around 15 C, so this should really be really say borderline. But it's enough. But it's close enough to room temperature to really make it much stiffer than its longer side chain cousins. Now, in order to rationalize the charge transport properties, we can look at the UV vis spectra as a function of side chain length. Now, Frank Spano at Temple University and others have shown that the UV vis spectrum can be deconvoluted into contributions from its vibronic peaks due to H aggregates. Those are ordered pi-stacked aggregates in the solid material, and also its amorphous regions, when added together, give you the full UV vis spectrum. And the point I want to make here is that C6 and C7 have almost identical aggregate behavior, and C8 is significantly worse than that, given the same thermal treatments. Now, the field of organic electronics has kind of been exploring the poly-3-alkyl thiophene for a long time. But if you add in the thermomechanical properties, we actually see some interesting and somewhat unexpected findings that poly-3-hexylthiophene has good hole mobility, or at least relative to the other two. Especially when you add in the PCBM, the hole mobility goes up. Decent efficiency. Now, these are efficiencies that are not state-of-the-art, but they are state-of-the-art when you're using only elastomeric components, so only stretchable substrates and electrodes. The glass transition temperature is higher, which gives you a high modulus and a low crack onset strain. Poly-3-octylthiophene has sort of the reverse behavior, where you're not very good electronically, but you are deformable, whereas C7 really has many green lights, so to speak. So you have good control over both the electronic and mechanical behavior. So to get some more insight into why these materials behave the way they do, we are trying to develop molecular dynamics simulations based on coarse-grained models. So what we did here was we took the atomistic model for oligomers of poly-3-hexylthiophene and then parameterized two models, a 3-site model and a 1-site model. In the 3-site model, this is the thiophene ring. Here's the first group of CH2 units, and here's 2 more CH2 units and the terminal methyl group. So each monomer is now 3 coarse-grained beads. And the 1-site model takes all of those components of the monomer and balls them up into a single coarse-grained bead, and that's what we have here. So what we found is that, so this represents a compromise between atomistic detail and computational efficiency. So what we found is that the 3-site model is actually the best one. So we can correctly predict the order of magnitude of the polymer using the 3-site model. We can also predict the trend in the change in tensile modulus with an increasing length of the side chain. We can predict, importantly, the glass transition temperature which is what you get when you plot density as a function of temperature, and the change in slope of density and temperature is where the glass transition occurs. We can also predict the anti-plasticizing effect of adding a fullerene molecule into the mix. So the mixture becomes stiffer as you add in the C60. And interestingly, and this was sort of an unexpected effect, is the effect of radius of gyration on blending with the fullerene. So we know that, that long extended chains have a greater propensity to entangle and make the material mechanically tougher and increase the extensibility and crack onset strain. But we know that adding the fullerene makes the material more brittle. So one explanation that came out of the coarse grain molecular dynamics is that adding the fullerene due to unfavorable enthalpies of association causes the poly-3-hexylthiophene chains to shrink. So we have a smaller radius of gyration in the blend than we do in the neat film. And that has the effect of decreasing the density of entanglements from 7 for the neat film to 2.4 for the bulk heterojunction film, given a degree of polymerization of 150 monomers. So that is sort of the end of our analysis for the polythiophene, but they're not really regarded as the future of organic photovoltaics. So what we did in collaboration with the Krebs group at DTU was look at a combinatorial library of 51 semiconducting polymers, which combine these 13 acceptors and these eight donor materials. And we took the cross products, and these were all synthesized as part of a previous study for viability in roll-to-roll fabrication by the Krebs group. But what we were interested in was the mechanical behavior and whether or not we could find some design rules that would predict the mechanical behavior of low band gap polymers. So this is a matrix with the donor on the y-axis and the acceptor on the x-axis. And we color-coded this in terms of favorability. So green materials are more favorable. So in this case, the tensile modulus is low, crack onset strain is high. And we can see some remarkable extensibilities. For example, D7A5 can be stretched to 57% without fracturing. You can find the details in our joint paper in Chemistry of Materials published earlier this year. And one thing we could do for fun was to combine this mechanical merit factor, which is just the ratio of crack onset strain to tensile modulus of the film, not the most rigorous methodology, but at least it gives you some idea of where one might start, and then multiply this by the power conversion efficiency, then find a relative merit factor between these materials and the standard, which is poly-3-hexylthiophene. And then if you have the data for all of these, now you need the mechanical data, as well as the photovoltaic data, then you can plot this relative merit factor, and we find that some of these materials are actually quite favorable compared to P3HT, which could be one of the routes toward identifying high efficiency materials for roll-to-roll production that also have good thermomechanical stability, and we have a few promising candidates. Now, what are the molecular design rules? Well, one of them that came out of this library was that isolated rings tend to be more mechanically robust than fused rings, and that kind of makes sense to us intuitively because they're more flexible, they have a lower barrier to rotation, and branched side chains tend to be more flexible or more deformable than materials with linear side chains. So, okay, I lied. We'll go back to the poly-3-alkylthiophene. So those are static properties. So tensile modulus, crack onset strain. What about cyclic loading? Can we learn anything from fatigue studies? So we stretched these materials many, many times to see what happened with the mechanical properties and tried to relate that to the microstructure that was determined by the weakly interacting H aggregate model. And we could find that over 10,000 cycles of applied strain to poly-3-heptylthiophene, particularly in the case where the material is stretched beyond its yield point, we see a reduction in aggregation behavior and a reduction in buckling wavelength. The reduction in buckling wavelength means that the material is becoming more compliant as it's fatiguing, and the aggregate fraction is going down. What's interesting is that it's also becoming more brittle. So the material becomes more brittle, more compliant, and this is potentially because of scission of covalent bonds. Typically in poly-3-alkylthiophene we find the reverse behavior, that low tensile modulus corresponds to low brittleness, but not in a fatigued sample. And here's our model. The as-cast film, higher aggregation, higher modulus. The fatigue film, lower aggregation, lower modulus, and increased brittleness. Again, possibly, well, first because of the reduction in aggregate fraction, but also possibly because of bond scission due to fatigue. And that's what we find also, that's what the engineering plastics community finds, of course, in engineering plastics. We also looked at the effect of the purity of the fullerene. So the energetic cost of purifying C70 PCBM is very high to get it from 95% pure to 99.9% pure, and that's just extracting the C60 from it. And we hypothesized that because C70 exists as a mixture of isomers, that C70 would have a lower modulus, and then mixtures, so technical grades, incompletely separated blends of C60 and C70 would have a lower modulus. And that's what we found. We also found that the power conversion efficiency didn't have much of an effect. Or the ratio didn't have much of an effect on the efficiency. So we can kill two birds with one stone here. We can use incompletely separated blends, which are cheaper to produce and cost less energy to produce. And interestingly, you can find this in our chemistry of materials paper, that the polymer is also less ordered with incompletely separated blends. We also looked at the effect of molecular mixing of the fullerene intercalated or not intercalated into different polythiophene materials, and and this has a well-known effect on the efficiency, which is why intercalated materials take a lot more fullerene loading to generate percolated pathways to the electrodes. But what we found is that the details of the microstructure didn't have much of an effect on the mechanical properties of the bulk heterojunction film. They were mostly determined by the modulus of the neat polymer. So that's a design rule for the future. You just are interested principally in the modulus of the polymer, and then worry about the fullerene later. So this is a project with Django May at Purdue, and the idea was, can we make a low bandgap polymer with flexible linkers? And these flexible alkyl linkers make the chain more flexible, but they also make have an interesting effect on the ability of the polymer chains to become closer and to interdigitate. To make a long story short, and you can find this in our macromolecular rapid communications paper, which is due out any day now, what's interesting is that the brittleness is actually the inverse of the partial inverse. I'm sorry. The modulus is the partial inverse of the lamellar peak full width at half max. And what's interesting here is that the stiffest, most brittle material, or that the most brittle material, crack onset strain of less than 4%, is actually the one with the greatest fraction of the flexible linker. And we think that's because the materials are getting closer. We can determine that by the size of or by the position of the lamellar full width at half max peak, and also the extent of interdigitation, which we infer by that, and also the order parameter. So the lamellar peak becomes narrower. And we don't take much of a hit on efficiency, but is this the way we want to go? Probably not. Probably this is not. Probably this type of main chain engineering with these alkyl groups linkers is not the way that we're going to maximize efficiency. So we also looked at semiconducting small molecules because there's an idea in the literature that, that polymers are the way to go for extensibility, but it turns out that the small molecules are nearly just as good when one considers only crack onset strain. Some of these materials described by Guy Bazan and Quinn Wynn's group, and this is actually a collaboration with the UC Santa Barbara team, are quite deformable. So the neat small molecule films are surprisingly ductile. Blending with the fullerene increases the stiffness and the brittleness, but the deformability can be partially recovered with diiodo-octane additives and also polystyrene additives, which increase the toughness. So there's an idea in flexible electronics that one wants to encapsulate a device so that the mechanically neutral plane experiences no strain. So the most fragile part of the device can be put in the mechanically neutral plane. Does that concept extend to stretchable applications? Probably not, but there is an analogy, perhaps not an analogy, but there is another mechanism that makes it favorable. So I told you about the importance of adhesion before. If you can have something that's adhered well on the bottom and on the top, then you can distribute strain across the whole film, and so that the strain won't be localized to thin areas and defects. So to show you an example, the P.PSS film under 50% strain has all of these cracks, as does the bulk heterojunction film. And when we put a layer of thermoplastic polyurethane on top, which is well adhered and distributes the strain evenly, we get no cracks. So we can rationalize this by this finite element model, which really shows the concentration of strain in the, at these programmed defects, and especially bad in the unencapsulated and delaminated cases. This is a vertical crack, pinhole defect, and thin area. Taking everything we learned from the stretchable applications, we can make the world's, I think the world's first all rubber solar cell in which every component, except for the fullerene, is actually an elastomer. So this is fully encapsulated, and we see the evolution in the photovoltaic properties as a function of strain. You can find this in Extreme Mechanics letters, which has now come out. We can make ultra-flexible solar cells also for wearable applications by taking all of the information that we've learned. If you account for both concave and convex buckles in the in bending and unbending of a device as it would be on the skin, you can see that we would need about 10% dynamic range of strain, which C6 will not survive, but C7 polythiophene will, and that's what we see. So C6 polythiophene gets worse as you bend it, as you compress it, like in this video, and C7 remains intact for up to and over 1,000 cycles of strain. Now this is a competition, or a superposition of the chemical degradation and the mechanical degradation, but importantly, the mechanical degradation seems to saturate relatively early, and the chemical degradation stays constant. And you can see that the device works, so it's powering a watch. So this is sort of a project. You can learn more about it in solar energy materials and solar cells. It sort of combines everything that we've learned about processing conditions and microstructure and molecular structure. And with that, I'd like to thank the team. Thanks also to Brandon Marin for helping with the production of this video, and a team of very talented PhD students, alumni, visiting scholar from JSR Corporation, undergraduates, funding from these agencies, in particular the Air Force Office of Scientific Research, NSF fellowships to several of my students, UCSD, the Hellman Foundation for the computational work, NDSEG for work for funding the work on wearable solar cells, and thank you very much for your attention.